Okay, let's go on to the test. And for this test, there are no confidence intervals that we need to calculate here, but we will have a classical approach. And when we have a classical approach, we need to specify critical values. Well, it turns out that for this particular test, the sampling distribution is a chi-squared distribution. And the chi-squared distribution for most sample sizes is going to be skewed to the right. The test that we use from 12.2 will only be a right-tailed test. We're never going to do a left-tailed test in section 12.2, and we're never going to do a two-tailed test. It's just a one-tailed test that we'll be doing. And the alpha in the one tail, is a relatively small number. Also on this, 0 is right there to the left. And then this is going to be your critical value. And then you're going to plot your test statistic along this scale as well for the classical approach. And then this would be the reject region. And then in here, do not reject. Now these critical values that you get will be on this table here. However, these right areas, we're only going to select small right areas. Now we don't want the right area to be 90% chance of making a type 1 error. We want the probability of making an error, our alpha, to be relatively small. So this is the right area. Not only that, in this test that we do, our degrees of freedom will be usually a smaller number. So most of the critical values for our problems will fall in this upper right quadrant of this table. But you read it in a way very much similar to the T table, where you have the column of degrees of freedom coming down the left column, and then the alphas up to the top. So if we do a problem that uses the classical approach, we'll refer back to this table. It's called a test for independence is one test, and then the test for homogeneity of proportions is another one. The one that we'll do most of is the test for independence. So what I'd like to do is to go through the 5 steps of the hypothesis test with you, and just point you to some things to look for here. First of all, the hypotheses, H0 and H1. For those hypotheses, the null hypothesis is going to be that the variables are not associated. We have 2 variables. And this null hypothesis in this section, we're pretty much going to write out into words. And so for our first example, we would say that gender and marriage happiness are independent. And independent means not associated in any way. The alternative hypothesis, which is usually our research hypothesis, is that gender and marriage happiness are dependent. And dependent means that somehow those variables are associated somehow or related somehow. There's a relationship. So these are going to be written in words, and you'll see how that works when we get to an example. You need to calculate these things called expected, I don't call them frequencies, because frequencies are usually whole numbers. I just call them expected values. And we need to calculate these in each case. I'll come back to this. Here is our test statistic. And you can see it's a chi-squared test statistic. And it's equal to the sum of a bunch of fractions. And the O refer to the observed frequencies from the data. And that is from a sample. And the E that you see here are the expected values. And using this formula up here, let's say from equation 1. Now here's what's happening in this. We have really one population in this first test in this section. And we take a sample, and from that sample, we have a bunch of frequency data. And we classify them like this, and we put them into a table. And so the sample size here would be n equals 24,455. And then we take those 24,455 and classify them according to two variables: how they responded to this question about being happy in their marriage and their gender. And if you add those 6 numbers, you get this 2455. But it is one sample. We just classify them according to two variables and put them in a table like this. So that's the scenario. Okay, so here are the, I'm not going to go through this in much detail, but here are your hypotheses. Level of significance, there's no change. You just go ahead and pick out the alpha. It's usually given to you in the problem. Step 3 is to calculate the test statistic and the p-value. Well, here's the test statistic, but as in the past, we're going to let the technology calculate the test statistic for us. And the calculator function that you want for this test is called the chi-squared test. And let me just show you where it is. It's in the same place. Hit the stat button and then go over to tests. And then if you scroll down, you'll pass all the ones that we've used up to this point, and you'll get to chi-squared test. If you hit enter, you have observed A, expected B, and then calculate. So it turns out that this input screen here for the chi-squared test never changes. What does change is what's inside A and B. Now, because A and B have brackets around them, in the calculator notation, these are known as matrices. So we have to put in a matrix into A and a matrix of the same size into matrix B. So if this was our data here, we would have 2 rows of data and 2 columns of data. And so this would be a 2 by 2 matrix. In our other example, here we have 3 rows and 2 columns. So we say that the dimensions of this matrix is 3 by 2. We always report rows first and columns second. And it turns out that the count data that you get from the sample, this is what we're going to put in matrix A, the observed values. And those are observed from our sample. In our test statistic, those numbers would be the O's. All right, so once we have that data into the matrix, then we can run this chi-squared test. There is a classical approach we talked about. Step 4, you can use the classical approach to make the decision, or you can use the same p-value approach. P is less than alpha, reject the null hypothesis. And then step 5 is always the same. My dog wants a treat. Okay, so here is the next test. and how you would write the hypotheses. You can see that it's 1, 2, 3 proportions. You could have more than 3 proportions here. But this is the second test. It's the test for homogeneity of proportions. But this is the second test. Also on your notes, it kind of takes you through how you use the TI-84 to enter in matrix A and then to run the chi-squared test. And the other thing is that when we reject the null hypothesis, the alternative, if in favor of the alternative hypothesis, it just means that there isn't a relationship between the two categorical variables. It doesn't say what that relationship is. So what we need to do is to look at conditional proportions of the problem to actually see what the difference is.